Waves, waves, waves. It's all about waves. But how do we represent them? After this problem, you will be able to identify waveforms and see how things appear different but are actually mathematically the same. And in this question, we wish to show that a to the e to the ikx plus b times e to the negative ikx and c times cosine kx plus d sine kx are the equivalent ways of writing the same function of x, and determine a constant c and d in terms of a and b and vice versa. Not too bad, but let's take a quick second to note that in quantum mechanics, when v is 0, the exponentials represent traveling waves and are most convenient in discussing the free particle, whereas sines and cosines correspond to standing waves, which arise naturally in the case of the infinite square well. Slightly different context, although these are mathematically the same. We have seen this discussion line before in Chapter 9 of Griffith's Introduction to Electrodynamics, so we are once again back with our old friends. So let's go ahead and dive in on how to solve these. Alrighty, so if we wish to write c and d in terms of a and b, we have to start with the exponentials. And that's what we see here. Color-coded, of course, because that's how we keep track of things. We know that we have two complex exponentials, so that lets us know we can use Euler's identity and then manipulate things with algebra. So for this exponential, it has a positive argument, so we know we have cosine kx plus I sine kx. This exponential has a negative argument, so we're going to have the same thing but a negative sign on the I. Not too bad, but now we can go ahead and distribute the a. So we do that here. We get a cosine plus a sine. We distribute the b into the second bracket, so we get b cosine minus bi sine. And as you expect from the color coordinating, we're going to group the sines and cosines together. And when we do this, we factor out a cosine. We get a plus b, positive a, positive b. And then we're going to factor out an a from the sines because we have an a, or excuse me, we're going to factor out an I from the sines because we have an I here and an I here. And then we note that this is positive a, so we report positive there. And this is a negative b, so we go negative there. And then we realize this is the exact form we're looking for. We see that this is equal to c cosine kx plus d sine kx, where c is reported back as a plus b, and d, the coefficient, is reported back as I times a minus b. So this one, pretty straightforward, not too bad. The next one's going to be a little more clunky, so let's go check it out. Wonderful. We saw how we were able to start with the exponentials using Euler's identity and then get the trig functions. Now we're going to have to kind of work backwards, starting with the trig functions. And what we're going to have to do is find how we can represent cosine and sine in terms of exponentials. And you guessed it, we're going to use the Euler identity once again. Recall over here that we have e to the I theta is equal to cosine theta plus I sine theta. Okay, so we have our cosine and sine there, but how do we get the cosine out of this jumbled mess? Well, we also have the negative argument side of things where we have a negative sign in the exponential, which leads to a minus sign here, which again we saw last time. No big deal. But now we can invoke some algebra. So if we add the two exponentials here, noting that the difference in signage on the I sine theta will allow it to cancel. So if we add here, we get cosine plus cosine, that gives us 2 cosine, and a positive I sine plus a negative I sine cancels that out to 0. So then we just divide over this 2 and we get something for cosine. And so when we divide over by 2, you see we get the form in the parentheses here, e to the positive ikx plus e to the minus ikx over 2. Good to go there. But what about sine? Well, if we could add these two yellow equations, we can also minus them. And that's what we see in the purple. E to the I theta minus e to the negative I theta. Well, that'll cancel out the 2 cosines. And the double negative here onto the negative here will make it a positive. So we get 2i sine theta. If we divide both sides by 2i, we get the term in the parentheses here, where we have e to the negative, e to the ikx minus e to the negative ikx all over 2i. Just like we did last time, we'll go ahead and divvy out and distribute the c in the 1/2, which we see here and here. What I'd like to take a note is that knowing how to use Euler's identity like this saves a lot of time. You'll see this, of course, in complex analysis course where you could just derive a whole bunch of equations. Honestly, instead of memorizing them, it's just easier to know the base equation and then to add or subtract. Much, much quicker in my opinion. And then what we can do here is distribute the c and the 1/2 into exponentials. So we have a positive exponential here and a negative exponential here, all with the c's. As the color coding will elucidate, we see that we have a positive exponential and a negative exponential. And guess what? The sign term also leaves us with a positive exponential and a negative exponential with d over 2i and minus d over 2i. So here, again, just like we did with the last slide, what we're going to do is factor out the positive exponentials. And of course, since we have a 1/2 here, we could factor that out as well. So we have a 1/2, which is multiplied by c plus d over I, and the positive exponential. Add that with 1/2 times c minus d over I with the negative exponential. Sure enough, we have some coefficient times a positive exponential plus some coefficient times a negative exponential, and that's exactly what we're looking for. We get a e to the ikx plus b e to the negative ikx. Wonderful. We see that these two things are working beautifully in harmony. Just again, understand the context that we have where exponentials are traveling, sine and cosine are standing, and then that way you can have contextual dependence on whatever you're dealing with in quantum mechanics. Real quick, on the note of reporting back to coefficients, we don't like i's in the denominator, so we do a trick called rationalizing them. So we multiply d over I times I over I, and the I over I, or rather the I squared in the denominator gives us a negative. So that's where we get this factor here. Similarly here, di times I, or di over I squared, that gives us another negative, so double negative gives us a positive, and that's why we report it as such. Again, we like to rationalize everything, but not a bad problem, one that we'll see again, and one that we've certainly seen before. So we'll wrap this up. As always, until next time, happy learning.